Okay, today is the Irish version of mechanics that Hamilton brings us. I looked for a green shirt to wear to honor the Irish culture, but it's the best I could come up with, spinach. But I don't think Hamilton's going to complain. The main thing that we want to do is make connection also with the fact that Lagrange is making use of velocity, and velocity is a contravariant quantity that goes with a covariant metric. And that makes it simpler for algebra most of the time, and I'll be showing you that. We'll go through the calculations for the polar coordinate Coriolis centripetal force analysis, single particle, 2 dimensions in polar coordinates with Hamilton. And you'll find that in doing that, it's not superior to Lagrange. Hamiltonian has other things that it does better than Lagrange, so it's important to know there's no such thing as a single tool for physics, and this is a perfect example of that. And we've got more equations coming. In the next lecture we'll talk about the Hamilton-Jacobi equations, and there are always the Riemann equations, which we will be getting in Unit 3. And those are the ones that work in general relativity, and there it's fully covariant, contravariant. So anyway, I want to go through that. It's something that we just have to do, and it's the guts of our algebraic approach. Now, one of the things Hamilton mechanics does really well is effective potential, so we'll spend a good deal of time today on that, and then we'll show some simulations of that. And we may get to be able to do a little bit with pendulum analysis that is kind of neat, something that lets you see what Hamilton equations really are geometrically. Anyway, we've been through this a number of times. Well, let's again see the zeroth equations, these two, again today. They make use, and also the first equations of Hamilton. That's right at the beginning of the derivations of his work. So this geometry is hiding in all of the stuff we do, and that's basic review that I want to have you remember. Now, and this is the same as that slide, and I'll leave the center one on for a while to compare with. And of course the weather analogy that we talked about last time involving Coriolis effects that give really monstrous storms, but virtually all of our weather depends on that. Let's see if there's anything I can do here. As I pointed out, we'll be doing the derivation very shortly here, so I'll put that up on that screen right now. And we'll go ahead with this one to start that derivation on both of these screens, so we can compare various things and we do it steps. The idea of having an explicit function of velocity is key to the Lagrangian, and the general curvilinear coordinate statement of that involves the velocity with its indices up the contravariant side of things. And what we're going to be doing in the process of making Lagrangian equations into Hamilton's equations is transforming the thing from covariant to contravariant variables. And how you do that is coming up here. But we're going to do something else. At this point, I want to mention that you could have very easily a Lagrangian problem that involves something that's an explicit function of time. Lagrangian then is an explicit function of position, coordinates of some kind, velocity coordinates to go with them, and then the fourth coordinate, which really is a coordinate in relativity, but here it's just a parameter. So this expression here that involves the total derivative and giving you a chain rule, in our case summing over two coordinates, r and theta, and then the velocities associated with those are dot and theta or phi dot, and then finally a fourth term here. The fourth term is just a single partial derivative, but it is something. It's the mad scientist meddling with a motion that would have been described very well by just this much. So somebody's meddling with the thing, somebody's fussing with the parameters somehow, and of course just about every one of our experiments that we do, particularly it's quantum mechanics, but I'm thinking classical mechanics, you shine a laser at something, you're meddling with it, right? So that laser would have an explicit time dependence, and first it would just be a cosine if you're doing a coherent state. But in any case, let's take that into account. Then I'm just saying, as the differential equation is being solved, I'm the mad professor turning various parameters within that equation. And we'll talk a little bit about what, there's some neat ways to do that, and Hamiltonian sometimes helps with that. Let's review here the equations that we're talking about in the past few weeks, the past few days anyway. This is an easy to remember set of equations. In our case, with our polar coordinates, we've got two kinds of momentum time derivatives. We've got two kinds of coordinates, r and theta, or r and phi. And we've got two equations that really only differ by where you put the dot. You can put it here, that's the first equation. You can put it here, and I have the second equation. Now, Hamiltonian equations are not quite that simple. So that's going to be one of the differences, but they kind of look like that, and you can see on the wall what they look like right now. Well, let's go ahead here, because that's what we're going to be deriving. We're going to be taking this chain rule here and converting these quantities there, which are, as they stand, these are covariant, not contravariant. The contravariant being in the denominator makes it covariant. I maybe haven't mentioned that enough yet, but that's the basic idea here, is we're going to be making this time derivative a combination of momentum and momentum dot. The p's are now ruling. And then we're going to rewrite this as a derivative of the product, which it is. This is just a good old product rule here. So that gets us very close to having the Hamiltonian function. And you see it there. I'm going to go ahead and put it here as well. All we have to do is switch this total derivative on this side with a partial derivative on that side, make an equation involving that, and rewrite it with the partial derivative now on the right-hand side, and the total derivative of L on this side, with the signs all being taken into account. So basically this is giving you the Hamiltonian function in the form that we talked about it when we were just doing the geometry of it. The product of momentum with velocity, that action formulation, and then subtract the Lagrangian. That's the good old the good old Legendre transformation between H and L. And this is the H right here. And there's the time derivative, total time derivative of it, being equal to the partial derivative with respect to time of the Lagrangian. Now that's where you see right away the advantage of the Hamiltonian. The advantage of the Hamiltonian is if the Lagrangian, and by, as we'll see, the Hamiltonian is independent of time. That is, if the mad professor has fallen asleep or it just doesn't exist, this guy, that's this guy, is a constant through the whole motion. So this guy only changes when this madman here wakes up and turns a few knobs. This will then change. That's going to be our total energy, but ahead of that, ahead of knowing that, it's worse. So we have a constant here that really is looking at the time dependence of the system and giving you either, yes, this is conserved, so I don't have any dependence in the Lagrangian of time, because I won't have any in the Hamiltonian either, and this will be a constant. Okay, so that's a big advantage that we can make use of. So this is just an identity that is really important for what we're doing here. So, and this is the Legendre transformation, good old-fashioned thing we talked about, using geometry as a way to introduce it. Here we're doing all of the algebra that's necessary. Okay, now just recall with these quantities, we have no dependence of the Lagrangian on momentum, and we have zero dependence. It's the zeroth equations of Lagrange and Hamilton respectively. We have no explicit dependence on velocity, q dots. They are constants as far as the Hamiltonian is concerned in algebraic sense. So what we can do then is look at the partial derivative of the Hamiltonian here, that's this thing, with respect to the momentum, and that's not zero. It's equal to, and we go right away to look at this thing, and we see right here a momentum. So we get immediately the partial derivative of p with respect to p. That, and then the partial derivative with respect to momentum of the Lagrangian is absolutely zero. So we have, by just looking at that thing, the very first Hamilton equation. Okay, so we've seen this already. This was what we got by geometry. The p gradient of this Hamiltonian is the velocity of whatever component you're talking about. And we have two here for the polar coordinates. Okay. Now the next step is to note that we've always taken for granted, without even saying this is a zeroth equation, that the partial derivative of momentum with respect to position, they should be independent. So that is definitely zero, technically zero. And also the partial derivative of q dot, that's a velocity with respect to the coordinate, also identically zero. So with that, adding that into this, we can take a look at the expression here of the transform, that is Legendre transform, momentum and velocity product there. Well, the partial derivative with respect to the coordinate of the Hamiltonian is 0 times 0, so that's out, and we're left then with just the partial derivative of Lagrangian with respect to q. You know what that is, partial derivative with respect to q is p dot. But with a minus sign. That's the cool thing here that makes this thing. I say cruel thing actually because this makes it harder to remember these equations. Which one has the minus? Okay. Well, I'll give you some ways to see that physically fairly shortly. But for now, there they are. So we're going to have two equations involving the first here, just like we had two equations involving first up there, and then the second down there, same thing, in our polar coordinate analysis. And at first it might seem, well, pretty much you're going to get the same thing, same amount of labor and all of that, but that is not quite true, as we'll see here fairly shortly. Okay, what I may do here is put one of these screens way ahead. So it's catching up here with us, and I think I'll take it back just for now. There's the results that we're dealing with right now. Okay. Is there anything else anything I've missed? I think we've got it here. I did mention one thing here. This is part of Hamilton's equations. We don't have that. This is something that makes a connection with Hamilton and Lagrange. the total derivative of the Hamiltonian is minus the partial derivative with respect to time of the Lagrangian. That's weird. That's really cool. But it's the one that lets you have the conservation of this thing if this turns out to be 0. Then the total derivative of Hamiltonian is 0, too. Constant. Very valuable. Okay. All your quantum mechanics works on having this. All the basic quantum mechanics, Hamiltonian. Now, what does the Hamiltonian look like in weird coordinates? That's the next step here. And our example is polar coordinates, so it's a good place to start. And we have to note that we're dealing with, in the Lagrange world, covariant metric. And remember that we showed that was a product of Jacobians. We'll be doing all of that again, so I won't go back and belabor those points. But basically what I'm going to be doing here is replacing the momentum in the Hamiltonian expression with velocities. You say, hey, you can't do that, it can't be explicit. Well, you're right, it can't be explicit dependency, but you can get the numbers. The numbers should still come out for this. The equalities should be valid if I replace here the momentum that used to go here, and then I go and I do the same thing with this. I write this expression in terms of velocity as well. So I get a fight between this thing, which is almost the same as this thing, except for a factor of a half, and I end up, as I write these two, just with 1/2 mv squared, basically. That's what it is, but it's the metric covariant and then the contravariant velocities. So this is sort of saying, we haven't done anything here numerically, and this is correct numerically, but it is definitely not correct for functionality. It doesn't have the right functional dependence that makes the calculus possible. So what we have to do, and this is just go back and replace this with the expression that converts, and this is really cool, is the metric coefficient converts momenta, canonic momenta, into velocities, provided you take into account a scale factor that involves the mass that might be traveling around in this coordinate system. And we're imagining there's just a single mass in our polar coordinate analysis, and I'm doing that right here. So this expression numerically correct, but formally not. This one, both correct. Numbers are right, and we're getting the energy if everything works out, and we're getting a constant if there's no explicit time dependence. So that's pretty much what we are. Now the details of the metric tensor analysis, I'll just skim through. This is something you should study. Make sure that you're able to pull this off. And this is where I ask you to, just for beginning tensor analysis, to draw little lines between things that are being summed here. And I've even drawn the lines from the metric here where they belong. So this is a sum over two things right there, and then there's another sum, so you've got over 4 sums just for that, and then you've got a sum here involving these two, the momentum and the metric. So just, that's part of the tensor analysis that goes with all of this. So this particular one is really easy. These are inverse of each other. We showed that just with the polar coordinate ones, but it's something that's pretty easy to bring. This is the whole idea of an E contra dot. An E co is usually 0. It's the delta function. So the two worlds, the red world and the blue world here, are getting together and making something. It's very simple. This is just a delta function right here. So you're ending up here with, again, momentum dot velocity, but in tensor notation. And let's see if there's anything else. This is the just another relation of velocity and momentum. So I can take that equation and write it out pretty nicely, and I end up with a contravariant metric sort of winning out right here, and involving momentum squared, and then the potential, which you're supposed to remember, not a function of momentum or velocity, on the coordinates. Okay, so this is what the polar coordinate Lagrangian turns into. Well, this is what it is in polar coordinates, and the idea is the this is right here. I'm going to go ahead on this frame here and get that stuff up front. These are the quantities that we're talking about that were involved in the algebra here for the polar coordinates. So you've got a covariant metric, it's diagonal. You've got a contravariant metric, it's diagonal, but has functions, in this case, only of r, no angles involved here. And then you've got the invariances in between those two. It's just a unit matrix, good old delta function. Delta function written in covariant, that's the lower index, contravariant, that's the upper index notation. So that's worth making a point of. Once again, we've talked about this before back on in lecture 9. Okay, this is making sense. I want to zooming through some algebra here at a really high rate of speed, but questions are welcome. We don't have to go at supersonic speed all the time. All right, let's see if there's anything else that I need. This is pretty much a good description of that for the polar coordinates. Now, equations, that's the word that gets a little dicey, a little sketchy. Actually not. When it gets used to what's happening, it's fine. But it indicates that the Hamiltonian is not the first method that you should attack an ordinary classical mechanic problem like the ones that we'll be doing. We'll be doing the trebuchet. We'll be doing little examples of spinning levers, or all kinds of things, mechanical devices that are fun to play with, both mathematically and in simulations. Even, well, if you play tennis, there's lots of mechanics in that involved. But you don't use a Hamiltonian to start off. Lagrangian's going to win almost every time with what we're about to do here. In any case, let's just go through Hamilton's first equation and Hamilton's second equation, the one with a minus sign on both the r and the phi coordinates that go with the polar coordinate thing that we're doing. And it's listed at the top here. The two equations for r and phi are pretty obvious. This is just the velocity, and this is just the velocity of the phi. Radial velocity, angular velocity. Okay, that sounds like we're pretty much like what we had back in the Lagrangian discussions. This one's got a minus sign on both. Okay, so far all we've got is some nice symbols. So that we have to actually do the partial derivative. If we're going to talk about a partial derivative with respect to PR, then we better write it out. Partial derivative of h with respect to that guy. 2 cancels the 2, leaves me with momentum divided by m. Well, okay, that's fine. Next step here, partial with respect to p phi, right there. Also not so bad. 2 cancels that, 2 leaves me with the angular momentum divided by, well, rotational inertia. So we're getting some of the things that the Lagrangian gave us immediately. It's coming up immediately here. And the same thing sort of is true with respect to the coordinate derivatives. Here r, okay, I'm looking for all the r's that I can find here, there's none there. Got to do something about that. Ends me up with -3 instead of -2 power here. gives me a minus 2, which cancels that 2, and leaves me with this thing, which is the angular momentum squared now divided by r cubed. We haven't seen anything like that in the Lagrangian description, you see. And then, of course, if I have any r dependence, I'd better take account of it in the potential. If the potential is not a constant with respect to r, then we better do it. And the same thing is going to be true when I talk about the angular dependence. This is asking for, do I have any lumps in the radius of my potential? Most of the time you will, but maybe it's cylindrical, spherically, or something symmetric, angularly symmetric, then you might not have this at all, but if you do, you've got to take it into account. So this is the second equation now, asking us about the partial derivative of u with respect to r. Now let's see if there's anything I need to say. That's okay there. All right. Okay, so next stop. Once we have PR, we might actually go ahead and see if we can relate that to velocity, and that's pretty easy to do. Here's PR dot now. That relation, okay, I've got this r cubed here, which is kind of weird, but it should settle out in the end here. And this thing, actual dot associated with that, if I look at this equation right here, I'm seeing that I have a change in angular momentum in time that's minus the phi gradient. Well, that's kind of different from what the Lagrangian was giving us, because this minus sign now that comes from there is what we're used to. That's a physicist gradient, right? The physicist has a force, that's a change in momentum, given as a minus the gradient, minus the derivative with respect to the coordinates. So that's coming out here now. It wasn't quite that way with the Lagrangian. And then I go ahead and I use that. I can go in here and take PR dot, mass is a constant, but I can get an R dot dot out of that and get an expression there for R dot dot. I'm going ahead here and using the P phi squared to give that expression right there. And I've got to do a similar thing with these two to get an expression. Finally, we're getting something we recognize from the Lagrangian approach. So this is where we make the, shall we say, pedal meet the metal, rubber meet the road. We see whether all of this gives us the same thing that we had when we were back doing the Lagrangian and writing the equations, particularly these equations here, the actual P dot. Now see that this one comes in simple stages. Here we're just taking partial derivatives to get expressions, but finally I've got to take a total derivative of each of my quantities. In the case of momentum, that's absolutely essential. That's what's driving everything. So this is pretty direct. Do the partials and then do two total derivatives and immediately get the result. Here we have to fuss around a little bit more. Now you've got to realize that fussing around goes up exponentially. So whatever happens over there that's 4 or 16 times more complicated in that example is going to come out much more in this one if you use the Hamiltonian. Okay, so they're the two together showing that. Now, what are the advantages for Hamiltonian, if any, for digital computer entry? Okay, most of the problems that we do in real world are not analytically solvable. We have to go to the computer. So Runge-Kutta is the workhorse for most of that sort of numerical analysis. And it's worth pointing that out right at the beginning. Runge-Kutta form, as shown there, is if you can get the equation involving whatever number of variables have, whether they're momentum, velocity, or anything, or whatever, get the time derivative of the first one, the second one, the third one, and so forth. In terms of the variables themselves, we do that pretty nicely with the Lagrangian. With the Hamiltonian. The Hamiltonian is already good in the sense of giving, oh sorry, I went too fast there, giving us radius dot, that's just PR over M. That takes care of this guy, and it's the only variable used in that first line. Second one is PR dot, what is it? Well, it's P squared over R cubed. That's that weird term, right? But here it's coming right out in the open, and Lagrangian, you have to work at it a little bit to get that. And then phi dot, okay? It's coming out nicely in terms of P phi and R squared. Maybe I should kind of have that from Lagrangian. And then this one, P phi dot, well, it's nothing but minus partial with respect to phi of u. So there's a nice set of computer equations. The computer will eat that and not give you too much trouble. Okay, so that's an advantage of Hamilton right there. Okay, that you should keep in mind. And by George, most of the things you're going to be doing are not analytically doable. So, what I also like to do here is give you another thing that Hamiltonian mechanics, and you've probably seen this one already, and this is called the effective potential. That's something that Lagrangian doesn't give you, not unless you turn it into a Hamiltonian, really. So this is an important contribution of Hamilton to all the physics and chemistry and engineering put together. So we've already made a fuss about Lagrangian telling us that a momentum, say P phi, will not change, that is, be a constant if the partial derivative of h with respect to phi, the variable in question, canonically conjugate to that, is zero. There's no dependence of phi. Then this guy will be zero. And having a constant like that is really nice. But here's the thing Lagrangian doesn't give it. The Lagrange expression for the L equal is not a constant if I am in almost any situation. So if I have a problem I'm solving where the mad professor is fired and he's not going to disturb his system, then this is constant. That is the Hamiltonian. So we've got two things that are constant here. First of all, the derivative of the Hamiltonian, but also the actual value of the Hamiltonian, the energy, total energy, is constant. So, big deal. This really is a plus for the Irish way of doing things here. Mr. Hamilton wins on this one, going away. So basically what happens is we go ahead and replace the P phi squared here, and as I say, you've probably already seen this if you've done any sort of quantum mechanics with atomic orbitals. This is the first thing you do. And so I replace that constant L here, the variable P phi is no longer part of the story, so I only have R and its momentum in an equation that is constant. Big deal. Okay, that's particularly for complicated coordinate systems. This is what we look for in hopes of getting an analytic solution. And this is true not just for our harmonic oscillator. I mean, this is a nice example, which we'll compare that to the Coulomb today here by doing simulations. But basically what we've done here is we've got the kinetic energy, we've got the total energy, and then we've got this weird potential that's only a function now of one variable, and that's the radius. So the actual real potential is whatever this is, and it's any spherically symmetric potential, not just harmonic oscillator R squared or Coulomb 1 over R. Those are both perfectly good candidates for this, but anything, R to the 217th power, it's spherically symmetric, so I'm good to go with this formalism in that case. And that's pretty powerful. That has really made atomic and molecular physics analytic in cases where you might not think it would be. So solving for the momentum is what you do once you've got this. You just basically have to figure out what PR is from this. It's a square root of that stuff right there. It involves functions of just the radius, r squared. So there's your radial momentum written out. And you solve the problem if that's all you want is the radial momentum as a function of where the particle is from the origin. And right now we're doing the harmonic oscillator, but we'll do the Coulomb, at least synthesize it, show the movie of it later. But here I can go ahead and I can take this a little bit one step further. I can get the velocity, radial velocity out as a function of the radius. That's pretty cool. And then it's just a matter of integrating. Well, it might be that the integral is pretty hard to do, but that's the equation. That's the radial velocity equation right there. Get all this stuff here on that screen. There's the radial velocity, and then what I can get out of that is time as a function of radius, which is a kind of clumsy way to get things, but that's the way we're going to do most of our orbits when we get to the Coulomb department, but also for oscillators and pendulums and the cycloid pendulum and things like that we'll be doing in just a next lecture or so. So this is a key thing, and the integral has a name. It's called the quadrature. Now where did that come from? These are all things that you just read it in a book on mechanics and they just say, we'll do the quadrature integral. This is the quadrature. Where does the quad come from? And basically what it is an integral between the smallest radius and the largest radius. And for our oscillator, that's a quadrant. And that's where it came from, I think. Anyway, integrating over a quadrant is giving you the time it took to go that quadrant, but it's also giving you, you can do an integral up to any radius and essentially back out the solution r of t, which is what you want. Okay, so that's a key part of mechanics, reducing complicated problems to quadrature is an expression you'll hear, and this is the best I can give you etymology of that particular terminology. Okay, let's see if there's anything else we can do here. Well, there is. We can actually show some pictures of the harmonic oscillator looked at in this way. Look at that in this Hamiltonian way. Okay, and remember we've got a real potential here that's r squared times the constant, spring constant over 2. So it's a Hooke's law oscillator IHO problem in isotropic harmonic oscillator, what that means. And then the centrifugal barrier. That's this thing that goes up like mad here because it's inverse r squared. So here's the real potential right here. It's just a parabola in R. It's a cylindrical parabola. It's a surface of revolution of a parabola. Paraboloid is what you get. But in the middle of this thing is this blue spike here, okay, which is also rotating with a revolution. So there's this great big spike in the middle of what was just a parabola before, and that spike gets fatter and bigger as you go to different values of the relative constant here. How much angular momentum are you going to tolerate in this problem? If it's none, this is gone, and you just go cruising through an ordinary harmonic oscillator back and forth in any direction. But most of the time, the interesting problems involve having some angular momentum in a two-dimensional orbiting situation. Okay, so that's what I'd like to go ahead and show in the simulation here of an independent isotropic harmonic oscillator doing its thing. So I'm going to go ahead here and click on this thing, oscillator potential PE, IHO should give us a pretty good picture of what we've already done very easily. This was done very easily the ellipse there was drawn very easily by drawing two circles, one with the apogee, that's what we just passed there, and then another one with the perigee, with a perihelion and an aphelion that's bigger, and that we understood very easily. This is a Cartesian view of an oscillator, a very easy way to see it. But this is the view in the radial coordinate with the shall we call it, effective potential, the whole, this thing mostly dominating in this neighborhood, but it dies off and becomes the actual potential if you go far enough off for low values of the angular momentum. Higher values you got to go further, and up here you got to go way up here before you get back to the original parabolic potential. Now this is a fun thing to play with. You can set your initial position and velocity by clicking and then showing a little arrow here that indicates the initial velocity. So I'll just start with something that's there, and we'll go with it and see what it does. But every time I was changing my initial conditions, I was changing this picture. So there it is, going to its apogee, then there's its perigee, and then it goes to the apogee again. So this is just an apogee-perigee diagram showing where the particle is at any given moment. Now there's something else going on down there. We're plotting here the momentum, Cartesian momentum, and what you notice is a little red ellipse that's congruent to this one. Now remember, we went through that before. Remember, all of our orbits, if you got rid of the omega factor, omega squared, omega cubed, all of our orbits that we drew, first a coordinate orbit, but it was the same orbit as the orbit of the velocity, which was the same as the orbit of the acceleration, which was the same as the orbit of the jerk, which was the same as the orbit of the inauguration. Now we've gone 4 derivatives and we're back home. Remember that little discussion? Okay, so you can expect this orbit right here to look exactly in form, not in magnitude, as the one in PX-PY space. Okay, so that sort of takes care of the oscillator, whatever you do. Now if I just drop this thing here, well, what I get is this program usually doesn't handle that very well. Actually, it did very well there. This one usually catches, right?
You've been known to hang, yes.
So it hangs up there, and then it's going fast. There, bounces, and comes through. Okay. And of course, if I start that with some velocity, give it a little velocity, then we've got, and you can see I can make something that's really, here's something that's not going to oscillate its radius at all. Not much at all, okay? This one is just changing the radius by a tiny little bit. And you can see I'm making a very big fat ellipse. It's quite, has a lot less eccentricity than the other ellipses that we had there. And we're almost about to finish it. So there's 2 apogees and 2 perigees for this kind of problem. You're up twice and you're down twice in a single orbit. Okay? And this is just tracking the radius as a function of time. Okay, well, that's, shall we say, fun for the feeble-minded. Let's get something that's a little more interesting, shall we say. I will exit out of that and have a look at the next thing here, and I'll do it on this screen as well. That's the oscillator that we just talked about. Let's try this situation where we have a 1 over r. This is outside of the sophomore physics Earth, so to speak, and the other one is the inside of the sophomore physics. These are orbits of the neutron starlet. that are being drawn there. But let's go ahead to this guy. This is got some more structure to it. And as I say, this is something we don't really treat, so I'm giving it time now before we get to chapter 5, where we do orbits in all their glory, particularly Coulomb orbits. But let me see if I can get this one to start up without blowing up the computer. Yeah, here we go. Now there are a couple of ahas right here. This is something where when you do simulations, you discover some things that people, most people that taught mechanics don't know. They can do the algebra for a problem like this, but did any of them know that you make a perfect circle with the momentum vector? That's cool. That is cool. And it's true. That's what it does. This is part of the O4 symmetry that hides in the oscillator potential, I'm sorry, the Coulomb potential, the outside of the Earth, as far as our sophomore physics Earth goes. Okay. Anyway, you treat this animation the same way you do any of these. I pick a point I want to start at. I draw an arrow here, and I have the ability now to go far enough with my vector here to just dump this thing out. This orbit, you can escape from this orbit. And that's the way, there's one of the ways to do it. This thing is just going to go out the door down to right there and never come back. So that's the difference of this thing. This thing is escapable, and remember there's escape velocity for the Earth. Anyway, I'm going to start this thing about there and see what we get. Bang! And then we fly up to the aphelion. There's one aphelion, we just passed it, and now we're coming back for a perihelion. When we go by the perihelion, zap! That's when you go around the circle really fast. Isn't that cool? So Coulomb's got a lot more structure to it than oscillator, but they're also intimately related by symmetry and other things we'll talk about later on. But in any case, of course, a circular orbit for this thing is found by setting your energy somewhere near the bottom of this thing. I'm just going to try to set it really close to the bottom there. And now I've got more or less uniform motion. It's a little slow there, a little fast there, but that's what this one's doing, okay? So these are things that you can play with later on. You're probably not going to remember all of this today, but these are always available in the lectures to play with.
Sorry.
Yeah. Oh, yes.
Yeah. What is the equation of motion in momentum space?
This is momentum space right here.
Right. What is the equation of motion?
X minus a squared plus y minus b squared equal r squared. That's it.
I mean, we already have kind of
You get a circle.
R.
When you get to the bottom of any one of these, you're going to get a circle, right? In space. But you're also going to get one in momentum space, and it'll be centered. That one isn't quite centered because this isn't quite centered. Mm-hmm. Now we're going to talk all about the geometry. By ruler and compass, we derive what's called the lens vector. You ever heard of that? Lens Pauli.
It's much better.
It's this Laplace, Lagrange, Sam the bartender down the street. I mean, everybody's name is on this thing. But very few of them realized that the vector was the eccentricity vector, and that was one of our discoveries. And then we made the geometry. You can calculate that thing with a ruler and compass. So it's based on that particular conservation, not just of angular momentum, but also of a vector called the eccentricity vector. Mm-hmm. So to answer your question, it's group theory. That's the real equation of the Coulomb orbit, the group theory of eccentricity plus angular momentum. And they're commutative, so that's an O4 symmetry, orthogonal in 4 dimensions. We'll talk about that later on. That's something that, I thank you for the question though. And then I'm saying, not quite any answer here. We gotta wait.
But aside from the group theory, I thought that the comparison between them is nonsense because that one is in space, that one is in momentum space.
Yes.
And the thing that doesn't have any symmetry in space has sort of symmetry when it has ellipse or circle in momentum.
You're saying that most of the orbits that we do up here lack symmetry.
No, that one.
Oh, this,
Yeah,
right here. Well, of course, we're only doing the radius,
right.
you see. So we've cut out the important parts,
Uh-huh.
which is this thing going around, right?
Right.
And sometimes it goes really fast,
Mhm.
right? And meanwhile, this is doing whatever it's going to do back and forth on the, well, it's kind of trapped there, so it's not moving much at all. I can make it circular by simply setting him right at the very bottom. And of course, I didn't quite get it, but that's good enough for folk music right there. That's a good circle. Okay. How good is it? It doesn't look so good for me. What's going on here? I'm going to erase the paths that I've already made here. Just look at, oh, it's a good circle. I was seeing something else. Okay, so obviously this is what would be called a LZ orbital in atomic physics, where you have all of your angular momentum is possible turned on, and this thing doesn't have any radial. This would just be a wave function, a little lump there. Does that help at all? So it's weird stuff, and there's all kinds of weird relationships between this and the oscillator, which were discovered by some people that have very long names. Kustenheimer-Stiefel relationship between the oscillator and the Coulomb. Anybody ever heard of him? Or her? I don't know much about the history. It goes way back. Okay, I'm going to back out of this after fixing it so I don't burn out the CPU here. I will pause and back out. We've got some other things to talk about. We've got the time to do it, I think. I do want to remind you that the sophomore physics earth problem, which you've done a little bit of, I'm disappointed some of you didn't go and make a better drawing, but this is about as good as you could get. Here's the angular momentum, and there's the potential to go with it. There's the potential for the thing outside, and then inside. You see, they connect in this problem. Your Coulomb outside, your oscillator inside. If you're a neutron starlet, okay, you can make that fantasy work for us. Okay, and remember the 3-step. Most people got that right. So this is all back in lecture 6, and there's the stuff that went with it, which we'll be doing over again later on when we actually do orbits. But it's worth having it in front. Now I would like to do a couple of things here. Normally I'd stop here, but I rushed this a little bit. I'd like to just go ahead and do some of the, first of all, simulations that use phase space, and that's what Hamilton is really looking at. That's what Hamilton is really thinking about to make his way of doing mechanics. And it doesn't hurt to go and look there. Crushed earth there. Okay, I have something called catcher in the eye. I also have some pendulums and things like that that are worth looking at. I think maybe I will start with, let's see if what it is that's coming up next year. Yes. Let's do the dull part of this first, but it's important to remember now that we have both, we have our tool box having not just the Lagrangian equations and the Lagrangian function, the difference between kinetic energy and potential energy, which would give you that polar equation there, if you just had the angle theta, and r was not changing, so this is a pendulum, a circular pendulum. The potential, again, this is the thing that gives the geometry of, I'll point on this thing right here, geometry that you see in every textbook that describes the force of a pendulum. That is, this little vector right here that is proportional to this times the sine of the angle theta right here. It's parallel to that. Okay, so the geometry is fairly simple. The actual distance, r sine theta, that this moves out, well, that's pretty close for small angles to just r times theta. So the pendulum that we used to keep our time with in clocks, tick tock, is going back and forth on a circle, but the distance that it moves, which is the thing that determines the force on this, is very, very close to radius times angle. And so that's a good approximation, is a harmonic oscillator. But we'll see it's not such a good approximation. Now, if you're talking about energy, that is how high this thing gets, the potential energy, that geometry, and this begins a Thales rectangle. I didn't finish the Thales rectangle. I did that for this one. This is the time geometry, where you're really interested in doing elliptic functions of half angles. So these are three different geometrical approaches represented by these diagrams right here. But whether you use Hamiltonian or Lagrangian, well, that's not such a big deal, really. But you got to be careful, because it's this incredible, shall I say, common locus or loci, plural of locus, of plus and minus sign blunders. Okay, the first one might be that you don't put the minus sign on the potential when you have a cosine theta there. That is one of the things that can go wrong here. But the idea, of course, is that the Lagrangian is a difference, has a minus to u, the Hamiltonian has a plus to u, you see. So we finally end up with the minus sign on the cosine, whereas this one's got it on the plus sign on the cosine. Okay, so then stuff that we're going to do with this is coming later, but this is a picture of the Hamiltonian as a function of its phase space. I think this is very enlightening, and it's courtesy of the Macintosh graphing calculator, I believe. If you have any computer now, practically, Ron Ivitsu, I don't know if I get the name right, worked for Apple for a long time, and he made this program long before it was easy to get three-dimensional graphing with lighting and all that kind of stuff. This is 25 years old, but now he still sells this on virtually all computer notes. It has, I think, an HTML version, but I'm not sure about that. Anyway, this is the phase space. Looking down from above, you see a bunch of circles turning into quasi-ellipses. This show this. I want to also show Hamilton's equation in a way that makes some sense of the minus sign that's in the Hamilton's equation. So minus sign that goes on the partial derivative of the Hamiltonian with respect to coordinate, this little guy down here. But if you look at the simulations that we're going to be playing with, particularly in the next lecture, the vibration region of a pendulum, where you can really trust the pendulum, is just a few pixels in radius. If you want 1% or 1/10% precision, you really can't go very far. You can't go even out to there and go around. Now this is the actual phase space, so it's left-handed, in the sense, when I'm up here, I've got positive momentum, that means I'm going to positive theta. So left-handed is the direction of flow for this diagram, and this diagram over here, which is now showing you how these topography lines translate into altitude, that is, into Hamiltonian magnitude, as a function of momentum in the theta direction and actual angle theta. So same plot, same thing, all I did was take this plot and Ron's program, and you paste it onto whatever surface he has programmed, or you have programmed, and it shows up like this. So these kind of diagrams are really easy to make using now modern computers that you guys all have. So to point that out, it's not so easy. And I encourage, at any point in this course for doing problems, you find the best graphing thing you can to do that, because that's going to stand you in good stead when you're building stuff for whatever research project you're on, or making papers for that, or finally your dissertation, right? It makes people really happy in a dissertation committee to see a good diagram. So this is an example of a pretty good diagram. Done a long time ago. I could do better now. Let me see if there's anything else I should say. This is what I call catcher in the eye. You guys are all too young to know who's the author, the catcher in the rye. This is where you would imagine you had control of the Hamiltonian in such a way that you could move the phase space loops like these. In this case, they actually are ellipses. This is a harmonic oscillator in 2 dimensions with different values in one and the other. But anyway, the idea is if you could control that, that is, if you could move the parabola that I asked you to study as an electric field coming and moving charge. You remember that? You all remember that problem, right? And you put the field on, okay? And you have this shift. You have this linear shift in the potential as a function of distance. And you have a minimum that starts here and goes down a curve that's the same shape as this, right? Where it started out right here, and then you move and increase the electric field, add a force y to y squared, basically, is all you're doing. Okay, so this particular thing has a simulation of, which I'm going to try to show here. It's going to be over here, so I might as well go over here and I'll take the other one back. That's the one that will have some action on it in just a minute, and I will go, well, I'll leave that one there for now. Let's just pay attention to this one. So here's the deal. What I've got is a charge that's oscillating because it's got some energy relative to the bottom of the well, charge oscillating and showing its positive velocity, negative velocity on a phase plot that's drawn right over this. So the question is, I can't stand that oscillation. How can I stop that? And there are a couple of ways to do it. One of them is to vary the, let's see if I can do it here, bring this thing over and basically try to trap the thing when it's, whoop, I've got to catch the motion. I've got to catch that moving dot there in the eye.
If you
okay?
square off and
I got to go boom over here. I got it smaller, but it sort of fooled me. Okay, I can catch it on the inside, right there. See, so I can catch this. I can reduce that oscillation by playing with the phase space variables. Now I can do this a number of ways. I can also increase the spring constant on this thing. which makes the orbit more eccentric. And sometimes it's easier to catch that one in the eye than it is the ordinary one. In any case, this thing is a neat playground there. I can just, stop the thing. Because now all it's going to do is orbit in the Hamiltonian orbits. But they're orbits in position and momentum. To really have power in controlling fast things, you've got to control the phase space, not just the force. Force is just going to probably make it worse. But the phase space, if you do it right, you can stop it. Now this kind of technique has saved lives. This kind of technique of using a phase space to stop a heart attack, where the fibrillation becomes extreme and chaotic, the whole system is just, you're going to die, okay? You create a machine that can find the nodal points of the phase space and put them where it is right now and then drop it back to center. And that is a much better way to stop a heart attack than the old way. The old way was to put a 1,000 volt, boom, and hope it stops. But you're probably hitting in a different phase space, and it may go on, and very often does, and finally the patient dies. But with this new thing, you just sort of feels where it is, goes for it, and the heart attack is over. So, the mechanics classical mechanics is not useless. Saves lives. So I hold that up as a really beautiful example of doing something like this. Now I think there are a lot of atomic and molecular experiments that can make use of this sort of approach. Okay, I'm going to back out of this one. I won't bother to try to stop it completely. I will be able to do that. See if I can do
Get a little window.
Oh, I did the wrong thing there. Let me get this going again here.
It's there.
There we go. There are a couple of things that I would like to show just before we go here today that I haven't quite mentioned enough here, I think. Well, that one is pretty obvious. I guess this is about all I want to do today. It's enough, I think. We've got the Irish under control, I think, right? Hamilton's equation, and then the use of his phase space. We've already done it when we draw little phasors for oscillation. We'll be doing that plenty again. But I think you get a better picture now of those two very separate worlds. The see if the UV laser is working. P dot, partial L with respect to Q, and then P without the dot, partial derivative of kinetic or Lagrangian with respect to Q, the coordinate. Those are our Lagrange equations, written not as cleanly as they are in the ones we've shown so far. But the Hamilton's equations, these guys, have this extra one. Total derivative of Hamiltonian is minus the partial L with respect to t. That minus sign that goes with the Lagrangian versus the Hamiltonian, you'll see that on the very back of your textbook where I put the relativistic versions of Lagrangian and Hamiltonian in a context that is a quantum diagram. So we're going to be talking a little bit more about that tomorrow. But in any case, you've got three sets of Hamilton equations. You really only have two sets, 1, 2, first and second of Lagrange. I'm not counting the zeros. That's my own funny thing. Now we still have a really hairy equation to consider. We won't be doing this one tomorrow, and that is the Riemann equations. Those are the ones that use full covariant, contravariant variables and what are called Christoffel symbols, Christoffel symbols, some people call them. So those guys right here and this stuff, that's for later. But we've covered a lot already. We've covered Jacobian, now the Lagrange equations, and also covariant, contravariant. And this is all in the review chapter. Okay, so we still have unit 2 and 3 to take care of more details and actual objects that are more complicated. So with that, we will adjourn 5 minutes early. That's always good on a nice day like this.